10, 9 minutes late. So the other day he was proving his proof. I told you no that I will come back to it again. Let x be an non-zero real number. Then x is equal to that formal limit a for some cosequence a n which is bounded away from 0. The proof is sort of, I thought, not clear. So you don't have to write. I will prove it on the board. See whether you can understand. After that I will give you copy so that you can take the board. So you know what we are going to prove is, I will write all of them. First, these are also important. Let A, B be real numbers. Then mod A is equal to mod of A minus B plus B. Certainly this is less than or equal to mod of A minus B plus mod B. You know mod of x plus y less than or equal to mod x plus mod y. Thus, you get from here mod A minus mod B less than or equal to mod of A minus B. Right? Now you can interchange A, B. A has no particular position with respect to B by symmetry. You get mod of B minus A also less than or equal to mod of A minus B. Whether you write A minus B or B minus A over there, no difference. So this is one thing we are going to use in the proof. Now let an n going 1 to infinity and bn n going 1 to infinity be two sequences of rational numbers. When you read the proof, by the way, if you are not convinced, you can ask me. Because always let A and B and B two rational numbers, two sequences of rational numbers. Then n going 1 to infinity is equivalent to, according to him, bn n going 1 to infinity. Actually, this is not how he writes. A and B are equivalent, doesn't matter. Then A and n going 1 is equal to b and n going 1 to infinity. If and only if you know the definition, no? For each epsilon greater than 0, there is this some n belongs to Z plus such that for each n greater than n, mod of a n minus b n less than epsilon. I mean, he writes less than or equal. Everybody else writes only less than, but it does not matter. Red pens is erased, no?
Yeah.
For each epsilon greater than 0, I mean, according to him, this is rational. A minus b n plus that epsilon cannot be seen. Hence, we are getting an going 1 to infinity and Bn n going 1 are not equivalent if and only if, you can tell me what that is. No? If A and B n are equivalent for each epsilon, there is a natural number I guess supposed to integer n such that for each n greater than n, n minus b n less than or equal to epsilon, then they are not equivalent.
For some epsilon greater than 0,
there exists epsilon greater than 0 such that
for all n belongs to 0 plus.
for all, say capital N belongs to say plus,
A minus b n mod is greater than epsilon for some n simple n greater than n.
there exists what you say simple n, no? Greater than n such that, right? A n and b n are not equivalent if and only if there is some epsilon greater than 0 such that this. So here you know about this absolute value of a minus absolute value of b less than or equal to absolute value of a minus b. Do you know that? We use this one to show that absolute value function is continuous. So we haven't come to continuity yet. Here I am talking about let A and B and be two sequences of rational numbers. Then they are equivalent means for each epsilon greater than 0 according to the book they are rational. There is an integer n such that for each n greater than n, n minus b n less than or equal to epsilon. That's a definition. From that definition, we derive this definition. Hence, A and B n are not equivalent if and only if there is some positive epsilon greater than 0, such that for all n belongs to Z plus, there is at least one n greater than n, such that A n minus B n greater than epsilon. Right? So here, here epsilon is anything. Here epsilon is something. Actually, that's what language he used for some epsilon greater than 0. So as a result, quite often when I teach, I put some epsilon 0. So it's not
Change.
It doesn't change. Yeah, exactly. It doesn't change. So in this proof, I am going to do it because it is important, not here. So now we are going to come to the what we are going to prove. According to the book, this is lemma 5.3.14. Let x be a non-zero real number. Non-zero real number. Then x is equal to some formal limit. If you have read it, you have seen this thing. Limit a n for some Cauchy sequence. A n going 1 to infinity of non-zero rational numbers. Of non-zero rational numbers which is bounded away from 0. Which is bounded away from 0. bounded away. That means if the number is 0 here, if 0 is here, the terms of the sequences are not the terms of the sequence are away from this interval, not close to 0. I mean, this is a fixed number. So we say this A is bounded away from 0. If and only if there is a positive number C greater than 0, such that for each n belongs to n, absolute value of n greater than or equal to C. It will not get close to 0 at all. So this is what we are going to prove. You know this thing now. So the reason I am writing the proof on the board is that I went through the proof with them in the book. I didn't feel comfortable, but I didn't say. I told them that I will come back to the proof. So I went home and wrote the proof. There is a little tricky thing here. I don't know whether it is done in the book. So I'm not going to worry about it. Now I'm going to prove it. Right, Buddha? You? Since x is real, x is equal to formal limit n going else to infinity dn for some Cauchy sequence Tuta, you are in which year OUSL?
I going to my batch is 21, 22, but I'm still in second year.
Second year. Okay, for some Cauchy sequence Bn n going 1 to infinity of rational numbers. This is not how I have introduced real numbers in your books, in the first year books, but this is a different way of introducing. I'm not going to answer. Tell x equals Bn for some cosequence Bn of rational numbers. This is by definition. Any real number is a formal limit of a sequence of rational numbers. But what we need is, we need a formal limit of sequence of non-zero rational numbers. Not only that, bounded away from 0. No? Bounded away from 0. That's what we need. Right? Since x is not equal to 0, now x is this one. 0 is 0, 0, 0, 0 sequence. So I have written here, hence An and Bn are not equivalent if and only if there is an epsilon greater than 0 such that for all n belongs to Z plus, there is an integer greater than n like this. So since Bn is not equal to 0, 0, 0, I will get where am I? Since x is not equal, we have Bn, this sequence n going 1 to infinity is not equivalent to 0, n going 1 to infinity. Right? Crystal clear. Thus, there exists epsilon 1. I will put a 0. It will not change. Epsilon 0 greater than 0 such that for each n belongs to n, for each capital N belongs to. I have written N here because that's what I am used to. Is it plus? There is simple N greater than N. There is simple N greater than N such that Bn minus 0 in absolute value greater than that epsilon 0. If I want, I can write epsilon 0 by 2. It is so I will write here 2 epsilon 0. It doesn't matter. What matters is the number here is multiplied by 2 here. That's all. So it is not going to. Uta, you understand? That's not irrelevant. Doesn't play any role. So I will call this is a star. This line. Thus there is epsilon 0 greater than 0 such that for each n belongs to 3 plus, there is simple and greater than n such that Bn minus 0 greater than 2 epsilon 0. This is very important in the proof. It says you have some number epsilon 0. No matter which capital N you use, integer, you can find another integer greater than that integer, like that Bn minus 0 greater than 2 epsilon 0 I do. I said call this statement, let me, the way I have written here, call this statement star. Call this statement star. Right? So for the proof, now there is an epsilon 0 positive number in this proof. That's not going to change. If Bn is also won't change, x won't change. Other things are changing things. Alright. I will call this statement star. I call it star. So since Bn n going 1 to infinity is Cauchy. Cauchy Bn n going 1 to infinity is Cauchy. There exists I again put n1. That's also not going to change. There is n1 belongs to Zn plus such that for each nm greater than or equal to n1, if you want, let's use it greater than n1, it doesn't matter how it is used, bn minus bm less than or equal to epsilon 0. So this epsilon 0 came from here. I am using that epsilon 0. Right? That's very important. Can you see this? You cannot interchange. I mean, since Bn n going on to this one is Cauchy, you cannot write this statement before star statement. The epsilon 0 coming out of star statement, I am using in this statement. Therefore, I have to write this one first. That's very important. I am wondering whether he did it. Because, I mean, he does write things, I actually am very uncomfortable. But doesn't, they are like this. Okay, it follows from the statement then. It follows from star statement. Follows from the statement, follows from the statement. Star. Because what star statement says is, there is an epsilon 0 positive number, no matter which n you use, there is an integer simple and greater than n, like this. So, now I have an N1. In this statement, I am going to put, for in this statement, I am going to put capital N1. Right? It follows from the statement star. There exists simple N1 belongs to Z plus, such that simple N1 greater than N1 and Bn1 minus 0 greater than 2 epsilon 0. Do you understand? Because the star statement says you have epsilon 0 number. Now for the proof, if there is a number called epsilon 0, we are not going to change it. Epsilon 0 has a property. What is the property? No matter which capital N, no matter which integer capital N you choose, you can find a bigger integer n, like such that Bn minus 0 greater than or equal to epsilon 0. So in the place of n, I am using n1. n1 came from this statement. So if I choose n1, there is an integer b, simple n1 greater than n1. It follows from the statement there exists n1 belongs to z1 such that n1 greater than n1 and clear, no? So can you see, you have to write the statements in this order. It's like I don't know whether you read my logic books. Maybe he has read. Now, for instance, I wash my hand and I had my food and I had my food. I wash my hands. Two different meanings. First meaning is I wash my hands and had lunch, means because I wanted to clean my hand. I wash my hands for that. Then if you change the order, what it means is, because there is food in your hand, so you want to get rid of that. So two different meanings. It is like you put your socks and shoes. You put your shoes and then put socks. Two different meanings. It is like that. So here this order is very important. First thing is I got this epsilon 0 because it is not equivalent. Then I got this n1 because Vn is Cauchy. Then I went back to this statement. I applied in the place of n, I put n1. So now all are fixed. I have the given sequence rational number x, real number x, sorry. Then I have the sequence Vn. Then I have the number epsilon 0. Then I have some integer capital N1. Then I have little n1 greater than capital N1 with this property. Right? Since n1 greater than n1, we have for each simple n greater than n1. What we know is for each n greater than n1, we know this line. For one of them, I am going to use n1. Other one, I am going to use n. Since for each n greater than n1, then you have Vn minus Vn1 less than or equal to epsilon 0. It's very tricky. You just cannot write freely. I wonder whether he did it, I don't know. Right? Now what we know is this n1 is fixed, epsilon 0 is fixed. No matter which n you use greater than n1, this line is true. Now let n greater than n1. Now I am using a little integer n greater than n1. Observe that. By the way, did you understand that proof? I mean, I was just going through the statements the other day, but I said, I told you I will come back to it. Did you understand really?
I didn't feel it.
Eh?
I didn't feel it.
Yeah. Observe that. Now I am taking n greater than n1. Absolute value of Bn is equal to Bn1 plus Bn minus Bn1. Now I have taken a simple n greater than n1. So this is something we know for sure. Then I can say this is greater than or equal to Bn1 in absolute value minus Bn minus Bn minus 1. That's what I did at the, I have the absolute value of A minus B greater than equal absolute A minus absolute B. From that absolute value of this one greater than or equal to absolute value of this one minus absolute value of that one. However, absolute value of B in 1, I know is strictly greater than 2 epsilon. Absolute value of Bn minus Bn1 less than or equal to epsilon 0. Therefore, minus 1 greater than or equal to minus epsilon 0, which is equal to epsilon 0. Now I have to something, but if I have an integer n1, I have a positive number epsilon 0, which is a rational number. If you do any n greater than n1, absolute value of Bn greater than epsilon 0. So let me write it carefully. Thus, for each n greater than n1, absolute value of Bn is greater than epsilon 0. My epsilon sometimes looks something else. Epsilon 0. So, what do we want? We are on the way to find you are given a real number x be a non-zero real number, it is non-zero. We are going to find the Cauchy sequence in some Cauchy sequence of non-zero real rational numbers which is bounded away from 0. Because x is a real number, there is a sequence Bn of rational numbers. X is equal to limit Bn, formal limit. However, I have proved that I don't know the whole sequence is bounded away from 0, that we don't know. However, any tail of, I cannot use the word tail, did we discuss that? No. So, after capital N1, every term is bounded away from 0. Epsilon 0 greater than 0. So, now what I will do is, I will define a sequence. Now, define the sequence. In n going 1 to infinity as follows. Now, because that's what I have to do, no? I have to find a sequence An of rational numbers, non-zero rational numbers. That's not enough, which is bounded away from 0. And by the way, taking epsilon 0 to be rational, I don't know whether I have with me. How do I define, by the way? An is equal to, these are braces, when my braces looks like Dear gracious. And this like this, epsilon 0 for all n less than or equal to capital N1, and Bn if n greater than N1. Bn, this is my A. I have to find my n because to complete the proof, I have to find the sequence A. Now I have to find my A. One thing is very clearly, n going 1 to infinity is a sequence of rational numbers. That much is very clear. It's a sequence of rational numbers because this epsilon 0 is rational. There is epsilon greater than 0. But let me write the word rational. And Bn now, of course, rational. So the whole sequence is rational. It is clear that here I said clearly, now I am saying it is clear that for each n belongs to n, mod an, can you see, mod an up to capital N1 is equal to epsilon 0. Mod an after N1 is mod Bn. After N1, it is greater than epsilon 0. Therefore, I can say mod an greater than or equal to epsilon 0. Right? Thus, n going 1 to infinity. Thus, n going 1 to infinity is bounded away from 0. Part of the proof is done. Now I have constructed the sequence an. I have proved this much, bounded away from 0. Non-zero rational numbers part is also clear. Because if Bn greater than epsilon 0, Bn cannot be equal to 0. I mean, that goes without saying. Now I have to prove that An is a Cauchy sequence. Now let us show that n going 1 to infinity is Cauchy. So in order to prove this, to this end, to this end, if somebody is listening to this video, the person said, maybe the person will think I am using some English words not known to them. To this end, let epsilon greater than 0 be rational. Are you using a positive rational number? Since B and n going 1 to infinity is Cauchy, since B and n going 1 is Cauchy, there it is n2. There it is n2 belongs to Z plus, such that for each n greater than n2. Oh, if you want, you can write greater than or equal, it doesn't matter. Bn minus Bm less than or equal to epsilon. This is the meaning of the Cauchy sequence. Since Bn is quotient, there is an N2, after N2, any two terms are at the most epsilon, at the distance at the most epsilon. Let capital N is equal to maximum of N1 and N2. I have N1 here, N2 because of this is quotient I put. Now let Nm greater than or equal to N. Because what I am going to prove is that after capital N, if you take any Nm, distance between An and Am is at the most epsilon. That's what I am going to prove. Then Nm greater than or equal to N1. Right? If Nm greater than or equal to capital N is the maximum of these two guys. So Nm must be greater than or equal to N1. Thus, Bn minus Bm and An minus Am are going to be the same. When N and M are greater than N1, An and Bn are the same. Since Nm greater than or equal to N2, Nm both are greater than or equal to Bn minus Bm, certainly less than or equal to epsilon. However, Bn minus Bm is A minus A. No? Hence, A minus Am less than or equal to epsilon. I have shown now what I said to this N less epsilon greater than 0. I have found a capital N. After capital N, any two terms are at the most epsilon apart. Therefore, okay, you know that. Thus, for each Nm, thus for each M, Nm greater than or equal to capital N, absolute value of An minus Am less than or equal to 0. Therefore, N going on to infinity is quotient. I have done that part. However, now I want to say x is equal to this one. X is equal to the formal limit of A. That's the only part I haven't done yet. I have a sequence A, it is quotient I have done. It's bounded away from 0 I have done. It's non-zero rational numbers I have done. What remains to prove is this part. So, finally let us show that. Let us show that x is equal to formal limit of A. That's the only thing remains to prove. That is, let us show that A and B are equivalent. Again, so let epsilon greater than 0. once again, be arbitrary. It is crystal clear that I just wrote this thing. In proofs you don't use the word crystal clear, but I used it here. It is crystal clear that for each n greater than n1, mod of an minus bn is equal to 0 less than epsilon as desired. As desired. New English words. As desired. So that means, because formal limit of this one is equal to x, they are equivalent, therefore formal limit of this one is equal to x. Thus, hence, x is equal to formal limit instance a. That is the proof. Are there any doubts any place, anywhere? Because this is a very important one. I thought he had not paid attention. Can you hear? This order of the statements is very important. First you get epsilon 0. Then you get this line n1. Then you lose epsilon 0 and n1 to get little n1. So this order of writing is very, very important. Even I wrote this thing twice at home because I did not look at the book. I tried to do alone. So this is it. Is it clear now?
Yes, sir, but I have a problem with the definition of a real number. His definition.
This definition,
No,
yes.
his definition of a real number.
Yeah.
So he says the final term of a infinite sequence of rational numbers is a real number.
No.
Like n goes infinity, it's like the final term.
No. His definition is this now. His definition of a real number is if Bn is a Cauchy sequence of rational numbers, he defined this formal limit. I mean, this since x is real, I have it x equals Bn.
Yes.
That is how he defines real numbers.
Yeah, it's a Cauchy sequence. Still,
Yeah.
A is something. A is rational.
Yes.
Okay, so if I forget about the notations, that
Yeah.
means A infinity must be rational. No, it's not. A infinity, it's not the proper word to use, but still.
I am not getting what you are saying actually. Maybe you need to explain a little bit. He defines, first he defined as well numbers, then integers, then rational numbers. After all, completely in a completely different way, he was supposed to define real numbers. Actually, this is how if you use the Open University books, I cannot remember whether I know. Sorry, I have defined real number system by 10 axioms, not this way. But this is correct. What he is saying is correct. Every real number is the limit of a sequence of Cauchy sequence of rational numbers. So here when he writes formal limit, this I have a little mistake. Is it no? This is fine. This way. This is how he defines. So what is funny is there is no limit he has taken. So I am not that happy, but that's the way it is.
No, question is that simple A n is rational. No?
Yes.
So it feels like formal limit n should be rational.
No.
Yeah, that's the thing that it feels like that. That's the problem. I get.
No. I guess you are incorrect. Every real number is, forget about his
Yeah.
story. Every real number is a limit of a sequence of rational numbers. That does not imply real numbers are rational. Every real number, forget about what is on the board.
That's the thing. It feels like, I don't know if it's true or false. It feels
Yeah.
like when you're approaching infinity,
Yeah.
the according to the definition, the rational number converts to an irrational number. There's
No,
possibility. That's
no, it's absolutely wrong. Because 1 over n, you have a wrong illusion like this. 1 over n greater than 0. But limit is equal to 0. Limits are sort of peculiar things. 1 over n greater. For instance, 1 over n is strictly greater than 1 over n plus 1. When you take the limits, both are equal. Now, if you take, for instance, this 1.4, 1.41, then 1.414, all these are rational numbers. But the limit is square root of 2. No, I mean, this is, I should not write this way, but there is a sequence. No? All are rational numbers, limit is an irrational numbers. Limit is, concept of limit is something, it doesn't meet our expectations before analysis. So, after you get to know some analysis, then we change our world. No, it is like when you I guess all of you are going to go to US after Sunday. Now you think Sri Lankan food is tasty, spicy and this and that. But if by any chance either you get married to an American girl or you make American friends and you begin to go to American homes, then you may say, oh, American food is tasty. It is like that. So limit, it amazes. All the exciting things comes from this limit, no, in real analysis. All of them come from limits. It is like, even though you haven't done anything, so about limits, the funny thing. Suppose you have a sequence of functions f1 going from the 0, 1 interval to real numbers, not f1, fn. Fn is a function going from 0, 1 to infinity. And suppose for each x, limit n tends to infinity, fn x is 0. Right? If you fix any x, then you get the sequence of real numbers. No, if 1x, 2x, 3x. If you take the limit is 0. And suppose you can integrate, and so far you think, of course, you can integrate anything because you haven't done integration. And suppose you integrate 0 to 1. Fnx dx is, let's say, today is 2025. Let's say this much is enough. If no matter which function you integrate, answer is 2025. And suppose now, can you see at each x, fnx goes to 0. So, therefore, actually you can say limit of fn limit of Fn is f, no? Which is equal to 0. Limit of Fn is 0. So, if you integral of Fnx dx is 2025, then what is the answer for limit of this one? If you integrate any Fn x, integral of Fnx is 2025. Therefore, if you integrate this one, limit of Fnx dx, I am not asking the question precisely. I have a sequence of functions. At every point, if I integrate this integral of any function is 2025. Then what do you? Let's erase these things. I don't know. Can you see? I haven't taught for 20 years. That's why I cannot remember. Fn integral of any Fn is 2025. Therefore, integral of the limit of Fnx is how much it will be?
N tends to infinity or limit n tends to infinity?
Yeah, when I say lim, I mean the limit and tends to. If you integrate any function, integral is 2025. And if you get the limit and integrate, then the limit will be. Because naturally I am asking without thinking too much. Kuta, how about you? What do you think? The answer will be how much? You integrate integral of any function is 2025. Assume you have a limit also for Fnx. If you integrate that function, answer will be. If you don't think too much, what is the answer? 225. But that's not true. Actually, answer is 0. Answer can be 0. So that's why limits are very highly. When I teach analysis here, so far I didn't get the chance to teach analysis. I am trying to escape from the book. I always say, every day I say, when you do analysis, you expect the unexpected. That's what I say. You always expect the unexpected. Is this clear? This one?
So that means the formal limit n tends to infinity an is not actually equal to a infinity if I say the final terms. Two different things, no?
I'm sorry, actually I'm not getting.
If I say the final term of the sequence is a,
There is no final.
yeah, that's the thing. That's why I said there's a small problem. So
No, big problem. What are you going to say?
no, the thing is like, so limit n tends to infinity a can be rational or irrational, right? The formal limit.
No, formal limit is when you are given a real number, his definition is this, no, that's how we define, no, in the book. If you take any x he says there is a Cauchy sequence of rational numbers and he writes lim Bn like that. You are saying something different and still I am not getting. But it's very important to clarify it.
Calculating interval or something. I need to process it a little.
Yeah?
I need to process it a little bit more.
To you, is the proof clear? So, in the book, that day I was telling you twice or thrice that I will get back to it because I didn't feel very comfortable with this proof, because here this order of these statements, like you first put the socks and then put the shoes, is completely different from first you put the shoes and then you put the socks. So here it is very important that since x is not equal to 0, that line comes first, from that you get some epsilon 0. Thereafter you get an integer n1 because it is Cauchy, Bn is Cauchy. Then you use that epsilon 0 and that n1 to find the little n. Thus this coming from this order is very important. Now I suppose since I have proved it, these parts are not in the proof. I suppose because we are trying to stick to the book and explaining the book, you are not getting the correct message, I think. Trying to. Because he is right, he has written the book for the people, those who know this. You are learning from the book without knowing this. So to you it is hard time. මේක පුතා පොතොස් ගහලා දැන් මේ අර නෝට් එකමයි ඔය. මේකමයි. From this lesson, from this proof, you are understanding. You cannot just write statements here and there. This order is very, very important, and you have to check whether I have proved everything. According to me, I have constructed every n is rational. And I have proved it is bounded by 0, and I have proved it is n is Cauchy, and I have proved that formal limit means I have proved that an and bn are equivalent. Then formal limit of, since they are equivalent, formal limit of an must be equal to formal limit of bn. I think here you are proving the things on the exercises in the book. So I don't know, because he insisted, not really insisted, but indirectly he was insisting on using the book. So you are not getting the spirit of analysis, but of course this one is constructing real number system. I suppose it has been too much for you, it seems like that. Then you have the homework, then I will do that example, by the way, to show you. Because homework. Again, you guys were telling me the other day about now. I am going forward, you are, as far as the tutorials, homework is concerned, you are really behind. I was wondering how to, clear the gap. Now you have a problem with the limit. No, I mean, it is, I just discovered it's good. Because it is happening because you are not really trying to learn the relevant thing. Because you are really thinking of form, limit, this and that. Now shall I raise the book? Before let me do that example also before I go. Now let us look at this example. I take any n. I am going to construct a function 0, 1. If I take any n, 1 over n is certainly less than 1. Can be equal to 1 also. Then I am taking a triangle. This one is, here is 1 over 2n, no, in the middle point. I take the height 4050n. This triangle. So then what is the area of this triangle? This is my Fn. I go like this, go like this, go like this. This is graph of Fn. What is this area? Area of a triangle is
half into base into height.
1/2. Base is 1 over 2n. And then not enough. 4050n. Then you cancel n to n. This length is 1 over n. 1 over n over the length. So, can you see then when you cancel 2 to 2, you get 2025. So, if I say this is my Fn, integral of Fn is 2025. What is the limit of this one? Limit of this one will be, because as n increases, 1 over n decreases to 0. At the point 0, function is always 0. At any point here, what is the limit? If you take any point somewhere here, what is the limit of Fnx as n tends to infinity? This is my graph of Fn. I mean, if I want, I can write the equations. You can write, no, this is 1 over 2n, this is 4050n. You know this coordinates here are 0, 0. Here x coordinate is 1 over 2n, y coordinate is 4050n. You can write the equation of this line segment. Similarly, this line segment. Here, Fnx is equal to 0. So what is, if you take a x here, what will be the limit of Fnx?
Intensity of Fnx.
Yeah, I'm asking. Limit Fnx n tends to infinity.
So 0 is 0.
Can you say it is 0? Can you prove it is 0? If you take any x, say, I have to draw the picture clearly. I will take my 1 here, to make it longer, so I will take any x. After some time, 1 over n comes here. There you are learning, I don't know whether you learned already. Given any x, there is an integer n, such that 1 over n less than x. I guess it is a lemma or something in the book. When 1 over n's come here, then your triangle will be like this. Therefore, Fnx is, for this n, what is Fnx?
2025.
No. I took a x, then I took an integer n, 1 over n is strictly less than x. So my graph will be this way, and this way. So what is f and x? 0. So then if I increase n, 1 over n goes like this. For any x, there is an integer n. After that, f and x is 0. Therefore, limit is 0 for any x. Limit at this point is always 0. So, for this graph, integral of any fn is 2025. Limit at any point is 0. So, integral of limit and limit of the integral are integral is 2025, therefore limit is 2025. Limit of the integral is 0. Integral of the limit and limit of the integral are not the same. For this sequence you get 0 to 1 fn x dx is always 2025. However, if you take the limit, then if you take the limit also it is still 2025 because limit of a constant is constant. But if you take the integral of the limit, you get 0. Therefore, for functions, integral of the limit and limit of the integrals are completely different. Completely different. Do you see what I'm saying? So anyway, we will be doing that sort of thing. What is, I don't know because I am still following the book. No, still continuously I have to follow the book. Here in this course, he has defined real numbers as, he says, formal limit. Any real number x is the formal limit of a sequence. So I am very uncomfortable. Then actually he has to prove, no, given any x, there is a unique Cauchy sequence whose formal limit is x. I mean, so many gaps in this course. Though he used the book, I am not happy. But he has made a good effort. I don't think he has done this, what I pointed out to you. I don't know. So what to do anyway? We get close to 11, too much of time. But is proof clear to you? I guess you still don't have a good idea about the limit. See, every real number is forget about this book. I'm just talking outside the book. Every real number is this one. Every real number is a limit of a Cauchy sequence. But so many real numbers are not. I mean, every real number is a limit of a Cauchy sequence of rational numbers. But almost all the real numbers are irrational. Almost all of them are irrational. You will, when I say almost all, to you it is not clear as of now, but you will learn it later in the course. Another thing I think is, when you are reading the book, don't just read, you take a piece of paper and write it down. See whether it is correct. Now, when I studied, I read every line, I did each homework. I mean, that's how one will learn. Otherwise, you cannot learn. Then you will have just a vague idea. You have to make sure when you understand it, you understand. Maybe you cannot then. If I ask you, do you understand? Then you say you understand. But what it means, it should be that you understand every line at least. And eventually you got what we wanted. But doesn't imply you can reproduce it. That's the thing. So anyway, because we learn logic, I mean you guys are now reasonably good at logic, and you know this construction, at the same time some analysis, is a whole bunch of work, so I don't consider it is easy. But you really have to spend some, I guess, time, I don't know, whole bunch of things. I guess he has mixed up analysis and construction, so that's why you have this hard time. Because analysis, you don't have, I guess, time to concentrate on concentrate on facts which have the analysis taste. You are spending a lot of time with the construction, rational, irrational, real, this and that. You are good. However, there is another thing. So next day I will bring K.G. Winmore's book. It's a very simple book. You have seen it? No? He says, in the whole world, after doing all the calculus, you go to the university, you begin to do analysis, every student will have a very hard time. Because you are going to prove the things you know. You wonder why you are not to prove it, if you know it. So here he is mixing many things. So I disagreed many times with him about the book, but there are of course good things about the book, but I don't know. Now let's talk about, we have free time is fast also. Now I don't know, I gave you homework today. Maybe. I was wondering I should do some homework on the book. But that is again not good, because you learn analysis, not only analysis, even algebra, by your effort. I give you solutions, you don't learn. Now for instance, I proved it, no. The reason I decided to prove, I myself, just because of he has written certain things, I just went through. He has not mentioned, I suppose, the points I pointed out. So that is why, now homework I have come to, this is homework for today, 4.1.3. Now I am about to go to chapter 6, no? 4.1.3. 4.3. Far away. You guys have any suggestions? I can, stick to anything you say. Because without doing most of the homework, going this thing is not a good thing. You learn by doing the homework. I think the difficulty, you cannot get analysis points because this construction, you are spending your brain, I guess, quite a lot of time to this 4.1.3, let's see where I was thinking, however, doing at least kind of easy problems on the board which are not 4.1.3. Show that -1 times A is equal to -A for every integer A. I guess that's not difficult. Some problems will be hereafter. I should do some problems on the board. What do you think of it? 4.14 says, between any two distinct real numbers there is a rational. So I ask you, then this one says there is one, no? Now I told you this one says there are infinitely many rationals. But you didn't get that idea. Why? Because you are in the rush to go to the next proposition. No, I mean you take any two real numbers. Let's see whether you will get that idea when I draw the picture. Here is x, here is y. There is some rational. I told you as soon as I saw it, I noticed that given any two distinct rationals, there are infinitely many rationals in between. How do I know that? Between these two, this is also real. There is another. So let's say this one, Q1. Between these two, there is another one, Q2. Between these two, there is another one, Q3. There is another one, Q4. There is another one, Q5. Between these two, Q6. Can you see that? Infinitely many rationals. Here says there is a one. Another thing here he says, between any two distinct rationals, there is a rational number. Now you wonder, between any two distinct rationals, aren't there irrationals? This one says that also. How? That is a problem somewhere in the book. Like that you have to stop and think. But the reason is, book is not that way. Oh. Mami, kalau orang beriman, first day I guess I used the whole word. Utah, usah semua ni. Ini kata utah orang dapat kau kata tanker nak tu. Kata. Alright. Then Mama, I told you, he are told that given any two distinct rationals, there is a distinct reals, there is a rational in between. Then I told you that says there are infinitely many rationals between two distinct real numbers. Then I was asking you, are there any irrationals? How can I show that there is one irrational using that there are infinitely many irrationals? How can I? It is an exercise somewhere because I do some exercises. Because I read every exercise before I give you.
Even the irrational number is a real number, so therefore again between x and q there is going to be another irrational number and so on.
No, I want to show that between x and y there is one irrational number. How do you say?
I was talking about the next step. There are infinitely many irrational.
How do I show? Somebody give me two real numbers, x and y. I checked y is greater than x. Then if I divide by x, if I divide by root 2 or multiply by root 2, still that remains the same. Right? So here is root 2, here is root 2. And still there is a rational. Now I multiply by root 2 the whole thing. Now what do I know? X over root 2 less than 0 less than y over root 2. I multiply by root 2 x less than root 2 times q times y. Now I have here is x, here is y, I have root 2 times q. Root 2 times q, is it rational or irrational? It is? It is irrational. So I have brought between any two reals. There is an irrational number using the fact that between any two reals there is a rational. Like that you have to think. But anybody.